Salam and welcome everyone. So today we're going to be working on the question on the screen that says consider a container of volume 5.0 dm cube that is divided into two compartments of equal size. In the left compartment, there is nitrogen at 1.0 atmosphere and 25 degrees Celsius. In the right compartment, there is hydrogen at the same temperature and pressure. Calculate the entropy and Gibbs energy of mixing when the partition is removed. Assume the gases are perfect. So the first thing you're going to note is that this is actually a question from the Atkins Physical Chemistry 11th edition textbook. And this question was told to us like a story in different steps. First of all, they're telling us consider a container of volume 5.0 dm cube that is divided into two compartments of equal size. So they've told us of a full container, they've told us its volume, they've told us the fact that it's been divided into two equal parts. In the left compartment, there is nitrogen at 1.0 and 25 degrees Celsius. And in the right compartment, there is hydrogen at the same temperature and pressure. Then we're asked to calculate the entropy and Gibbs energy of mixing when the partition is removed. And we have to assume that the gases are perfect. So the first thing you have to do whenever you have a question like this is to write out all of the parameters. We're told a container of 5.0 dm cube. So the volume is 5.0 decimeter cube. And then we're told that we're dealing with compartment divided into two equal sides. The left compartment, there is nitrogen at 1.0 atmosphere and 25 degrees. So on the left compartment, we have the pressure of nitrogen gas to simply be 1.0 atmosphere. So this is the left side. Okay. And then we see that the temperature, we're told, is 25 degrees Celsius. So 25 degrees Celsius. We can just convert directly now from degrees Celsius to Kelvin. So 25 plus 273.15. So temperature is just the 298.15 Kelvin. And then the pressure of hydrogen gas, which is what is on the right compartment, is just the same as nitrogen. So it's just basically writing the same thing. So 1.0 atmosphere. The temperature is also going to be 298.15 Kelvin. Now, I want to quickly mention something. As you can see, we have solved for the temperature as well as, sorry, we have written down the temperature as well as the pressure of both of the gases, of both the nitrogen and hydrogen gas. But before we proceed, I want to quickly mention something. Since they're talking about volume, you may think, well, they already told us the volume, but they told us the volume of an entire container before a partition is put. So, what is now the volume after there has been a partition, or after the volume of the container has been split into two or has been divided? So, basically, what is now the new volume? So, this is a container. Just want to show you guys with a diagram. This is a container. This entire container is 5.0 dm cube. This partition now comes, okay, and divides it into two. You have the left side and then you have the right side. The left side here is where the nitrogen gases are. The right side is where the hydrogen gases are. So I'm just trying to show you. Now, what is going to be the volume of the nitrogen and the volume of the hydrogen? Well, since it's two equal parts, we can just simply divide the current volume by two. So the volume, okay, of nitrogen, okay, as well as the volume of hydrogen gas is just simply 5.0 dm cube divided by 2, which is just simply 2.5 dm cube. So this is going to be the volume of each individual compartment. So I just think it's very important that I mention that before we start solving. Now that I've written all of the parameters, they've told us to calculate the entropy as well as the Gibbs energy of mixing when we remove the partition back and allow the nitrogen gas as well as the hydrogen gas to mix. So what is the Gibbs energy of mixing? Okay. So what is the entropy of mixing? One. And what is the Gibbs energy of mixing? So this is what we're supposed to solve. So this again is from chapter 5 of the Atkins Physical Chemistry 11th edition textbook. And in the textbook, there is a formula that teaches us what the Gibbs energy of mixing is. So the Gibbs energy of mixing, okay, has the formula to be And this is in a situation where you're dealing with binary mixtures, meaning a mixture between just two components, for example, just between water and sugar. So in this case, let's say we're dealing with the component A and component B. This is just a general formula. We have N sub A, where A is the gas or the component A, RT, okay, or RT sub A, whatever you want to call it, plus it doesn't really matter. The temperature is just the temperature. Multiply by the pressure, okay, that is the partial pressure of component A of gas A divided by the total pressure, okay, of the mixture plus the number of moles of component B or of gas B multiplied by the gas constant times the temperature of component B or gas B multiplied by ln, the partial pressure of B divided by the total pressure. Okay, after the mixing. So this is basically the formula that we're supposed to use. Again, this is when you're dealing with a binary mixture between two different components. So this is the formula that we're going to use. But I want to quickly teach you guys something else. There may be a situation where rather than you using this formula, so rather than you using the pressure, temperature, gas constant, number of moles, you may be given a question where you're dealing with just mole fraction. Okay, so if they give you the mole fraction and of a particular so if you're given the mole fraction of or the mole fractions of different components in a particular mixture, you would be required to use another formula. So the change in Gibbs energy of mixing ends up becoming nRT, where n is the total number of moles, okay, and T of course is just temperature, and R gas constant, multiplied by the mole fraction of component A, ln the mole fraction of component A again, plus the mole fraction of component B or gas B multiplied by ln the mole fraction of component B or gas B. So this will be the formula that you have to use if maybe you're given the total number of moles as well as the mole fraction and you're asked to find the Gibbs energy of mixing, but you're not given any other information like pressure or volume. So this is the other formula you would use. So but in this particular case, let's focus on the first one. So I'm going to rewrite, what happened? So I'm going to rewrite this first equation, but this time around is going to be in terms of what we actually want it to be in terms of. It's going to be in terms of hydrogen as well as nitrogen. So the Gibbs energy of mixing is just simply going to be N. So this is for nitrogen. So N sub N2, okay, RT, ln, the pressure sub N2 divided by the pressure, total pressure, okay, plus N sub H2, okay, RT, or I can just say T can be temperature sub N2. But the truth is the temperature, okay, for nitrogen gas is going to be the temperature, same thing as the temperature for hydrogen gas is going to be the same thing as just the total temperature. You're not really adding anything. Temperature is one of those things that just exist. Like it's not like pressure where you're actually dealing with like force over area and things like that. In this case, temperature is the same, right? If you're in a particular room, the whole room, if it's hot, the whole room is hot, right? It's not going to be one section of the room that is cold while the other part is hot, especially if it's in an enclosed area without any AC. So in this particular container, you're not adding any other source of heat. You're not removing heat or anything like that. Does that make any sense? So the temperature is really the same. So you can just represent it as T. The truth is the answer is just going to be, the temperature is just going to be the same. So the temperature for nitrogen is the same thing as temperature of hydrogen because they're both in the same container, even though there's a compartment, is the same thing as the temperature of everything mixed together. The temperature is always going to be the same. So I'm just putting um T sub N2 and T sub H2 to make it easier for you guys so I can pick the picture of the two different compartments coming together in this particular formula. That's the reason why I'm doing that. So anyways, T sub H2, just know that if you choose to skip it, there is no big deal. So T sub H2, okay, ln P sub H2 divided by P sub T. So that's basically this one here. Yeah, so that's basically this. Yeah, that is it. So this is now the formula that we're going to be dealing with. But before we go on, we realize that we've only been given the temperature, the pressure, the volume. We already know gas constant because gas constant is a constant, but we're not given the number of moles. And in order for us to determine the number of moles, it's going to be like a much longer process. But as scientists, we can also try to make our work easier by thinking through problems. Remember, at the beginning of the question, we were told that we should assume the gases are perfect. So ideal gases that are perfect, same thing. So basically, we can use the perfect gas formula here. So PV is equal to nRT. Here, that is just the perfect gas law, okay? But we can now write this perfect gas law in terms of hydrogen as well as in terms of nitrogen. So to do that, we end up with P, okay, sub N2 multiplied by V sub N2 is equal to N sub N2, okay, R, and then T sub N2. So this is what this is here. We could do the same for hydrogen. So we have P sub H2, okay, V sub H2 is equal to N sub H2 R, and then T sub H2. So you see what's going on here is just telling you that rather than going on to solve for the number of moles by using the perfect gas law and then having a situation where you just have N is equal to PV divided by RT, and then you solve for what N is and then substitute and just make your work much longer and cumbersome, you can just simply substitute. You're allowed to do that. It's just like simple algebra, right? If you have, let's say, x is equal to y squared, and then you have a question where you're like, x over y squared, um, multiplied by z squared. How do you solve this? If you already know that x is equal to y squared, you just end up having y squared over y squared multiplied by z squared. You cancel this out, so you end up just having z squared. So I'm just showing you that this is just us going to apply algebra. And when we apply algebra, our knowledge of algebra, we can completely substitute nRT for nitrogen to be PV for nitrogen, as well as we can substitute the nRT here for hydrogen to become the PV of hydrogen. So this is what I'm trying to explain. So we end up having the change in Gibbs energy of mixing to be, rather than n sub 2 or n sub n2 r times t sub n2, we can just simply write P sub n2, so the pressure, the partial pressure of nitrogen, multiplied by the partial volume, and multiplied by the volume of nitrogen. Okay, that is just it. Multiply by, because this can be substituted with PV for H2 for N2, sorry, and this can be substituted for PV for H2. So we just substituted it, and when we do substitute it, we just end up with that information there. ln, okay, P sub n over 2 divided by P sub T, okay, plus P, okay, sub H2 multiplied by V sub H2, okay, ln P sub H2 divided by P sub T. So that's basically it. So yeah, we have this information now. We can just simply substitute. We've got the value for pressure, we've got the value for temperature, we've got the value for volume for each one of the gases. We've got the one for nitrogen as well as the one for hydrogen. So remember, the pressure for N2 as well as the pressure for H2 is 1 atmosphere, okay? And then the volume for N2 as well as the volume for H2, since it's two equal compartments, is just simply 2.5 dm cube, right? So we can just simply substitute. But then we are scientists and we know that physical chemistry just has to be a little bit harder than normal. So you know that you can just simply substitute, because if you look at our question, we are asked to solve the change in entropy of mixing as well as changing Gibbs energy of mixing. So what this is telling you is that our final answer has to be in form of joules or Newton meter. And in this case, we have our pressure to be in the form of atmosphere, and we have our volume to be in the form of decimeter cube. So that means we have to convert from atmosphere to Pascal, because Pascal is just simply Newton per meter squared, okay? And we have to convert our volume. So this is pressure, what we have to do for pressure. And then we have to convert our volume from dm cube to meter cube. That is what we have to do to the values before we can substitute, so that we can easily get our final answer in joules. So to do that, we've got 1 atmosphere, okay? is actually equal to 101,325 Pascal, or 1 atmosphere is equal to 101,325 Newton per meter squared. And then dm cube, we know that 1 meter is equal to 10 decimeter. So 1 meter cube, that's 1 times 1 times 1 will be 1 meter cube. And meter times meter times meter is meter cube. So that's the left side. And then we can also cube 10 decimeter as well. So 10 times 10 times 10 is 1,000. Decimeter times decimeter times decimeter is decimeter cube. So that's basically what this is. So yeah, that's basically it. So therefore, 2.5 dm cube is going to give us what? It's going to actually give us x. So let's find what the unknown is. So basically 2.5 decimeter cube in meter cube will end up becoming 2.5 times 10 raised to the power of negative 3, okay, meter cube. If you want to work on this personally to see that this is actually the correct answer, feel free to pause the video and do that. But I've done a similar question like this, the part B of this question, of this exercise, in a different video. So try and watch that as well in case you just want more clarification. So, anyways, so we have all that we need in order for us to substitute, right? Again, let me rewrite what we have. We have the change in Gibbs energy of mixing to equal pressure of nitrogen gas times the volume of nitrogen gas, ln P of nitrogen gas divided by P total, okay, plus pressure of hydrogen gas multiplied by the volume of hydrogen gas, ln P of hydrogen gas divided by pressure of the total pressure. So you have that. So let's simply substitute. So changing Gibbs energy of mixing, it's just going to be substituting the pressure. We've got 1 point. Okay, so substituting the pressure, sorry, we don't have 1.0 anymore. We now have 101,325 Newton per meter squared. Okay, that's for the pressure here. That's for the pressure here, multiplied by the volume, which is just simply 2.5 times 10 raised to the power of negative 3 meter cube, okay, multiplied by ln pressure of nitrogen gas, which is just simply 101,325, okay, Newton per meter squared, okay, divided by the total pressure. Now, I want to quickly mention something to you guys. Remember how the question told us that in the left compartment there is nitrogen at 1 atm, in the right compartment there is hydrogen at 1 atm. So basically they have the same thing. If you remember from Dalton's law of partial pressures, let me quickly explain this. Dalton's law of partial pressures just states that the total pressure in a mixture of gases, okay, like in this case, is equal to the sum of the partial pressure of each individual component. So in this case now, let's say we have component A and component B. So we're just going to add up the partial pressure of component A with the partial pressure of component B. In this case, we can just simply do that quickly. That's just going to be the total pressure. I forgot to add this in earlier. I apologize. So the total pressure of the total pressure is just the sum of the partial pressure of nitrogen gas plus the partial pressure of hydrogen gas. So it's just going to be 101,325, okay, Newton per meter squared plus 101,325 Newton per meter squared. And when you add them together, you end up getting 206,650 Newton per meter squared. So that's just going to be this particular information here. So this is going to be what the total is going to be. So we just simply substitute back into our calculation. So we have 206,650 Newton per meter squared. So that's basically how this is done. So we use that information to continue with our calculation. So we have all of this information here. Okay, so close brackets. We've done the one for nitrogen gas plus, now we're going to focus on the one for hydrogen gas, which is just simply the pressure of hydrogen gas is just 101,325 Newton per meter squared, okay, multiplied by 2.5 times 10 to the power of negative 3 meter cube, okay, multiplied by ln of the partial pressure of hydrogen, which we know to be 101,325 Newton per meter squared, divided by the total pressure, which is just what we calculated now, 206,650 Newton per meter squared. So yeah, we continue with our calculation. You cancel out all the units. So we've got Newton per meter squared. We have meter squared at the bottom here. So we cancel that out. We remove the meter cube. So we have just meter left. Then Newton per meter square here, cancel that out. Newton per meter square here, you cancel that out. In this case, we've got meter square here. We cancel that out. Meter cube here, we remove the squared from it and just have meters left. Then you have Newton per meter square, cancel that out. Newton per meter square, cancel that out. So what we end up having left is just simply, and again, before we continue, we already know that 101,325 is half of 206,650. So we can just cancel that out. 101,325 here, 1, and here is 2. The same thing here. Here, 1, and here is 2. So yeah, that's what we have. So what we end up having left is the Gibbs energy of mixing is just equal to 101,325, 325, okay, multiplied by 2.5 times 10 to the power of negative 3, okay, Newton meter, ln of 0.5, okay, plus the exact same thing again, 101,325 multiplied by 2.5 times 10 to the power of negative 3 Newton meter, ln 0.5. So that is basically what we have. So we input both sides in our calculator to get. So we end up with, on the left side, we have negative 175.58285 joules, okay, minus 175, okay, 0.58285 joules as well. Now you may be wondering, we're dealing with positive values. How did we get negative value? Let's not forget, because should have done this in pre-calculus. Anytime you take the ln of a number less than 1, or if a fraction or a decimal less than 1, you're going to have a negative value. So ln 0.5 is going to be a negative value, and the value is just simply negative 0.69315. So that is where the negative comes from. So that's what makes everything on the left side as well as on the right side negative. So that's what's going on here. And of course, you add them up. So change in Gibbs energy of mixing is just negative 175.58285 and minus negative 175.58285 joules. So when you do that, you end up getting negative 351.16569 joules. So this is basically the answer to this question. So yeah, this is basically what we've been solving so far. This is the answer. But then again, we're chemists. We already know that we have to put our work in the proper number of significant figures. And to do that, you have to look at our work and see what is the lowest number of sig figs. The lowest number of sig figs in our work, as we can see, is 3 sig figs. Sorry, it's 2 sig figs, right? We've got 5.0 is in 2 sig figs and 1.0 is in 2 sig figs. So the lowest number of significant figures, for those of you who do not know, is so for those of you who do not know, the lowest number of significant figures is going to be the number of significant figure our final answer has to be in anytime you're dealing with chemical or chemistry calculations. So in this case, our calculation involved us using the 5.0 dm cube and 1.0 atmosphere. They are both in 2 sig figs. So our final answer has to be written in 2 sig figs. So this is going to be in 2 sig figs. So change in Gibbs energy of mixing is just going to be negative 3.5, okay, times 10 raised to the power of 2 joules. And this is the answer to this question. Yep, this is the answer to this question. Negative 3.5 times 10 to the power of 2 joules. Now, let's not forget, we still have the other part of the question, which is the entropy of mixing. So the change in entropy of mixing, which we're supposed to solve for. So the change in entropy of mixing here It's very, very easy to solve. Since we already have the change in Gibbs energy of mixing, we can easily solve for that. So the change in entropy of mixing is just simply the negative of the change in Gibbs energy of mixing, okay, divided by temperature. So the relationship between the change in Gibbs energy of mixing and the change in entropy of mixing is just temperature. So change in entropy of mixing is just simply negative of negative 351.1659 joules, okay, divided by the temperature, which is just 298.15 Kelvin. So that's basically what that would be. We input this in our calculator. We end up getting positive because of the negative here, 1.1777815 joule per Kelvin. And of course, since we are supposed to solve our working proper number of sig figs, we're going to have a situation where we're going to convert this to two sig figs. So the change in entropy of mixing is just simply going to be positive 1.17, okay, sorry, positive 1.2. Remember, two sig figs. So positive 1.2 joules per Kelvin. And that is going to be the answer to this question for change in entropy of mixing. I want to quickly mention something for those of you who do not know. You can see what I did in this particular situation is that I made sure to use the raw values rather than the exact value of negative 3.5 times 10 to the power of 2. I used the raw value of negative 351.16569 purposely because whenever you're solving chemistry questions or science questions generally, you have to keep on using the raw value so that you can get your final answer as precise as possible. Do not use the approximated value to solve to do further calculations because it's not going to give you as accurate an answer as possible. So that's the reason why we have to keep using the raw values, even though we know what the approximated value is. We keep using the raw value to do further calculations, and then we approximate the new answer to the proper number of decimal places or significant figures. So that's just one thing I wanted to say. So if you're struggling with any of your STEM related courses, whether you're middle school, high school, or college, email me at shuhabitutoring@gmail.com. I help students succeed in all of their STEM related courses in academia. And if you have any questions, suggestions, or concerns with regards to this channel, the way I tutor, or just overall how to improve the channel, please put it in the comment section. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.